Tonight, we're going to explore something that seems like it should have a simple answer but doesn't. Why do space rockets need so much fuel? You've seen the launches, these massive vehicles, taller than skyscrapers, carrying millions of pounds of propellant, and yet the actual payload, the thing they're trying to get to space, is often no bigger than a car. Over 90% of a rocket's total weight at liftoff is just fuel. That ratio sounds insane. It sounds like terrible engineering. But here's the thing, it's not bad engineering, it's physics. There is a brutal, inescapable mathematical truth hiding inside every rocket ever built. And once you understand it, you'll never look at a launch the same way again. Before we go any further, if you find this kind of deep dive into how the universe actually works interesting, a quick like or subscribe really helps the channel grow. It's a small thing for you, but it makes a huge difference for me. Now, let's begin. Let's start with something you already understand: movement. You know how to move. You've been doing it your whole life. You walk by pushing your feet against the ground. The ground pushes back, and you go forward. You swim by pushing water backward with your arms. The water resists, and your body glides ahead. You ride a bicycle by pressing pedals that turn wheels that grip the road. In every single case, you move by pushing against something. There's always something there to push against: the ground, the water, the air, the road. This is so fundamental to your experience of motion that you probably never think about it. It's instinct. It's obvious. It's how the world works. But now imagine this. Imagine you're standing on a perfectly frozen lake. The ice is so smooth that there is zero friction between your shoes and the surface. You can't walk because your feet just slide. You can't run because there's nothing to grip. You're stuck. You're standing in the middle of this lake, and no matter how hard you try to move, your feet just slip. You're going nowhere. Now here's the question. Is there any way to move yourself across this ice without anything to push against? Think about it for a moment. Actually, yes. There's one way. If you take off your coat and throw it as hard as you can in one direction, you will start sliding in the opposite direction. You won't move fast. Your coat is light compared to your body, so you'll barely drift. But you will move. And that simple act, throwing something one way to move yourself the other way, is the entire foundation of how rockets work. Every rocket ever built, from the earliest Chinese fire arrows 1,000 years ago to the Saturn V that carried astronauts to the moon, operates on this one principle. You move by throwing stuff behind you. That's it. That is the only way a rocket works. There is no other trick, no secret technology, no exotic physics. A rocket moves by expelling mass out of its back end at very high speed, and the reaction to that expulsion pushes the rocket forward. This principle doesn't require advanced technology. It doesn't require fire or combustion or any particular energy source. It's far more basic than that. It's one of the most fundamental laws of physics ever discovered. This is Newton's third law of motion, published in 1687. For every action, there is an equal and opposite reaction. When you throw your coat on the ice, the action is the force you exert on the coat, pushing it away from you. The reaction is an equal force pushing you in the opposite direction. The coat goes one way, you go the other. The forces are equal in magnitude but opposite in direction. A rocket does the same thing, except instead of throwing a coat, it throws extremely hot gas out of a nozzle at tremendous speed. The gas goes backward. The rocket goes forward. The forces are equal and opposite. This might seem too simple to be the foundation of all spaceflight, but it is. And the reason it matters so much. The reason this simple principle leads to rockets needing absurd amounts of fuel is because of where rockets have to work. Space. Space is empty. There is nothing there. No air, no water, no ground, nothing to push against. On Earth, you have options. You can push against the ground with wheels. You can push against the water with propellers. You can push against the air with wings and jet engines. A jet engine works by sucking in air from the atmosphere, mixing it with fuel, burning the mixture, and blasting the hot exhaust out the back. The engine uses the air that's already there. It doesn't have to carry the air with it. It just grabs air from the environment, adds energy to it, and throws it backward. This is incredibly efficient because the atmosphere is essentially free mass. The engine only needs to carry fuel. The air, which makes up the majority of the exhaust mass, is supplied for free by the atmosphere. A commercial jet airliner can fly halfway around the world on a single tank of fuel because it uses the air itself as reaction mass. The fuel provides energy, but the atmosphere provides most of the mass that gets thrown backward. This is a luxury that rockets do not have. But in space, there is no air. There is no atmosphere. There is nothing to grab, nothing to heat, nothing to throw backward, except what you brought with you. A rocket must carry everything it needs to produce thrust. Every single molecule of gas that comes out of the exhaust nozzle had to be carried from the ground, loaded onto the rocket before launch, lifted through the atmosphere, and hauled into space. The rocket is like a person on that frozen lake, except instead of throwing one coat, they need to throw thousands and thousands of coats, one after another, to keep accelerating. And here's where it starts to get complicated. Every coat they need to throw later has to be carried now. You can probably already sense the problem building. But before we get there, let's make sure we truly understand the physics of how a rocket generates thrust. Because there's a common misconception that confuses a lot of people. Many people think rockets work by pushing against the air. They imagine the exhaust gases slamming into the atmosphere behind the rocket, and that collision somehow pushing the rocket forward. This is wrong. Completely wrong. And it's easy to prove. Rockets actually work better in a vacuum than they do in the atmosphere. If rockets worked by pushing against air, they would work better where there's more air and worse where there's less. But the opposite is true. In the vacuum of space, with no air at all, rockets are more efficient. The reason is that air actually gets in the way. When a rocket is firing in the atmosphere, the air outside the nozzle pushes back against the exhaust, reducing the effective speed at which the gases leave the nozzle. In a vacuum, there's no external pressure, so the exhaust can expand freely and leave the nozzle at its maximum possible speed. More exhaust speed means more thrust per unit of fuel. So rockets don't push against anything external. They push against themselves. It's an internal process. The combustion chamber generates extremely high pressure gas. That gas pushes outward in all directions against the walls of the chamber. But the chamber has a hole in it, the nozzle at the bottom. The gas that pushes on the top and sides of the chamber has nothing to cancel it out at the bottom because that's where the gas escapes. The result is a net upward force on the chamber walls. That is thrust. The gas pushing on the inside of the rocket pushes the rocket one way, while the gas itself flies out the other way. It's Newton's third law applied in the most direct possible manner. The rocket and its exhaust are pushing against each other, not against anything in the environment. Now, let's talk about a concept that's absolutely central to understanding rockets. It's called conservation of momentum. and it's one of the most fundamental laws in all of physics. Momentum is simply mass times velocity. A heavy object moving slowly can have the same momentum as a light object moving fast. A bowling ball rolling gently across the floor might have the same momentum as a baseball thrown at high speed. Conservation of momentum says that in a closed system with no external forces, the total momentum stays the same. If you start with zero momentum, you must always have zero momentum. This is exactly the situation on that frozen lake. Before you throw your coat, you and the coat are both stationary. Total momentum is zero. After you throw the coat has momentum in one direction, and you have momentum in the other direction. These two momenta are equal in magnitude but opposite in direction. They add up to zero. Total momentum is still zero. The law is satisfied. You can try this yourself in a simpler setting. Sit on a rolling office chair on a smooth floor and throw a heavy book across the room. You'll roll backward. Not fast because you're much heavier than the book, but you'll roll. If you had a stack of heavy books and threw them one by one, you'd gradually pick up speed. Each throw would push you a little faster. The more massive the object you throw and the faster you throw it, the more momentum you gain. This is intuitive once you think about it. But it has profound consequences for spaceflight because it means the only way to gain speed is to lose mass. This is precisely what happens in a rocket. Before the engine fires, the rocket and its fuel are moving together at some velocity. When the engine fires, some of that fuel is expelled backward at high speed. The fuel now has momentum going backward. To conserve total momentum, the rocket must gain momentum going forward. The amount of forward momentum the rocket gains equals the backward momentum of the expelled fuel. This is not optional. This is not a design choice. This is a law of nature as fundamental as gravity. You cannot gain momentum without something else losing momentum. The rocket gains forward momentum only by giving backward momentum to its exhaust. This leads to a crucial insight. The thrust a rocket generates depends on two things: the mass of exhaust expelled per second, and the speed at which that exhaust leaves the nozzle. If you throw a heavy thing slowly or a light thing quickly, you can generate the same momentum change. Thrust equals the mass flow rate multiplied by the exhaust velocity. Engineers often talk about a property called specific impulse, which is essentially a measure of how efficiently a rocket engine uses its fuel. Specific impulse is directly related to exhaust velocity. The higher the exhaust velocity, the more thrust you get per unit of fuel consumed. Different propellants produce different exhaust velocities. The space shuttle's main engines burned liquid hydrogen and liquid oxygen. This combination produces exhaust velocities of about 4,400 meters per second. That is roughly 15,800 kilometers per hour. The exhaust leaves the nozzle at that speed. It's fast, unimaginably fast compared to anything in daily life. A hurricane produces wind speeds of maybe 250 kilometers per hour. A tornado might reach 500. The exhaust from a liquid hydrogen engine is moving more than 30 times faster than the most violent tornado on Earth. But it's not unlimited. Chemical rockets are constrained by the energy stored in chemical bonds. When hydrogen and oxygen react, they release a certain amount of energy per kilogram. That energy gets converted into the kinetic energy of the exhaust gas. The exhaust velocity is determined by how much energy per kilogram the propellant can release, and how effectively the nozzle converts that thermal energy into directed motion. This number has a ceiling. The best chemical propellants we know of produce exhaust velocities in the range of about 3,000 to 4,500 meters per second. This is a hard limit set by chemistry. No clever engineering can significantly exceed it with chemical fuels. You might squeeze out a few percent more efficiency with better nozzle designs or higher combustion pressures, but you cannot fundamentally change the energy content of the chemical bonds. This is important because exhaust velocity determines how much fuel you need to reach a given speed. The lower the exhaust velocity, the more fuel you need. And the exhaust velocities of chemical rockets, while impressive, are actually quite modest compared to the speeds rockets need to achieve. Let's talk about those speeds, because this is where the problem starts to become vivid. To reach low Earth orbit, a spacecraft needs to be traveling at about 7,800 meters per second relative to the Earth's surface. That's roughly 28,000 kilometers per hour. That is not a gentle speed. That is extraordinarily fast. A bullet fired from a high-powered rifle travels at about 1,000 meters per second. Orbital velocity is nearly 8 times faster than a bullet. But achieving orbital velocity is not just about going fast. It's about going fast in the right direction. Orbit is not simply being high up. A satellite in low Earth orbit is only about 400 kilometers above the surface. That's not that far. It's roughly the distance from New York to Washington, D.C. The reason a satellite stays up there is not because it's above gravity. Gravity at 400 kilometers altitude is only about 10% weaker than at the surface. The reason the satellite stays in orbit is because it's moving sideways so fast that as it falls toward Earth, the Earth curves away beneath it. The satellite is falling, constantly falling, but the ground keeps curving away just as fast. The satellite falls around the Earth rather than into it. That's what an orbit is. Perpetual fall that never hits the ground because of the sheer speed of sideways motion. It's a concept that confuses many people, but it's absolutely central to spaceflight. Being in orbit is not about being high enough that gravity doesn't reach you. Gravity very much reaches you. Astronauts on the International Space Station experience about 90% of the gravitational pull they would feel standing on the ground. They float not because there's no gravity, but because they're falling. The station is falling, and they're falling with it. So, relative to the station, they appear weightless. The station just happens to be falling sideways so fast that the curve of its fall matches the curve of the Earth. It misses the ground endlessly, circling the planet once every 90 minutes at a speed of about 7,700 meters per second. To achieve this, you need to accelerate your spacecraft to 7,800 meters per second. But that's not all. In rocket science, engineers use a concept called delta V, which is the total change in velocity a rocket needs to provide. The delta V needed to reach low Earth orbit is not 7,800 meters per second. It's actually closer to 9,400 meters per second. The difference, about 1,600 meters per second, is eaten up by two enemies that we'll explore in depth later: gravity and atmospheric drag. For now, just know that reaching orbit requires roughly 9,400 meters per second of delta V. Your rocket needs to provide that total velocity change from the moment of ignition to orbital insertion. So here is the problem, stated as simply as possible. A chemical rocket produces exhaust at roughly 3,000 to 4,500 meters per second. But the rocket needs to accelerate to 9,400 meters per second. The rocket needs to go about 2 to 3 times faster than its own exhaust. think about that. On the frozen lake, if you could only throw your coat at a certain speed, but you needed to move faster than that speed, one coat wouldn't be enough. You would need to throw many coats, one after another, each one giving you a small push until all those pushes accumulated enough momentum to get you to the speed you need. Each time you throw a coat, you gain a little speed, but each coat you plan to throw later is still weighing you down right now. You're carrying the mass of all the coats you haven't thrown yet. That extra mass makes each throw less effective because you're heavier. So you need even more coats, which makes you even heavier at the start, which makes each early throw even less effective, which means you need even more coats. Do you see where this is going? This is the central problem of rocketry. It's not a bug. It's not poor engineering. It's a fundamental consequence of physics. When your propulsion system requires you to carry your propellant with you, and when you need to go faster than your exhaust velocity, the amount of propellant you need doesn't just increase, it skyrockets. Every additional kilogram of fuel you add to the rocket makes the rocket heavier. A heavier rocket requires more fuel to accelerate, but that additional fuel adds even more weight, which requires even more fuel, which adds even more weight. It's a vicious cycle, a self-reinforcing spiral that drives the fuel requirement up and up and up. This is why rockets are almost entirely fuel. When you watch a rocket launch, when you see that enormous vehicle sitting on the pad, you're mostly looking at fuel tanks. The actual spacecraft, the capsule or satellite being delivered to orbit, is a tiny fraction of the total mass. The rest is fuel. And fuel to lift the fuel, and fuel to lift the fuel that lift the fuel. The Saturn V rocket that carried Apollo astronauts to the moon stood about 111 meters tall. It weighed about 2,950,000 kilograms at liftoff. The Apollo spacecraft itself, the command module, service module, and lunar module combined, weighed about 45,000 kilograms. That means the payload was roughly 1.5% of the total launch weight. Over 98% of the rocket's mass at liftoff was structure and fuel, overwhelmingly fuel. Think about that for a moment. You build a vehicle the height of a 36-story building, fill it with nearly 3 million kilograms of propellant, ignite 5 of the most powerful rocket engines ever constructed, each one producing over 6.7 million newtons of thrust, generating a combined 34 million newtons, enough force to lift a small city block off the ground. And all of it exists to deliver 45,000 kilograms to the vicinity of the moon. If you wanted to bring a grand piano to orbit, you'd need a rocket that weighs roughly as much as a locomotive just to get that piano up there. If you wanted to bring a small car to the moon, you'd need something the size of a Saturn V. The numbers are staggering, and they are not exaggerations. They are the direct mathematical consequence of the physics involved. To put the ratio in everyday terms, that's like driving a fully loaded 18-wheeler across the country just to deliver a single suitcase. Except, even that comparison is too generous, because an 18-wheeler is maybe 20 times the weight of a suitcase, while the Saturn V was about 65 times the weight of its payload. Compare this to any other form of transportation. A commercial airplane like a Boeing 747 weighs about 178,000 kilograms empty, carries about 200,000 kilograms of fuel, and can transport about 70,000 kilograms of passengers and cargo. That's a payload fraction of roughly 16%. A cargo ship is even better. A large container ship might weigh 200,000 metric tons when fully loaded, with well over half of that being cargo. A car weighs about 1,500 kilograms and can carry about 500 kilograms of passengers and luggage. That's about 25% payload. A rocket manages between 1 and 5%. The efficiency compared to any other vehicle is appalling, and it's not because rocket engineers are bad at their jobs. It's because the physics of moving through empty space by throwing exhaust out of a nozzle is fundamentally, inescapably, brutally different from moving through an atmosphere or across a surface where you have something to push against. The SpaceX Falcon 9, one of the most efficient rockets in use today, is similar. It weighs about 549,000 kilograms at liftoff. Its maximum payload to low Earth orbit is about 22,800 kilograms. That's a payload fraction of about 4.2%. 95.8% of the rocket at liftoff is not payload. It's fuel and structure needed to get that payload to orbit. The space shuttle was even less efficient in terms of payload fraction. The entire shuttle system, including the external tank and solid rocket boosters, weighed about 2 million kilograms at liftoff. The maximum payload to low Earth orbit was about 27,500 kilograms. That's a payload fraction of about 1.4%. These numbers are not the result of bad engineering. These are some of the greatest engineering achievements in human history, designed by the smartest people on the planet, optimized over decades with billions of dollars of research and development, and they still end up being 95 to 99% fuel and structure. The reason is physics. The reason is that inescapable cycle of fuel, needing more fuel. The reason is that when you have to carry your propellant with you and you need to achieve a velocity that exceeds your exhaust velocity, the math gets brutal. We haven't even gotten to the equation itself yet. We'll get there. But I want you to hold this image in your mind as we continue. A rocket sitting on a launch pad is one of the most extraordinary things humans have ever built. Not because of how powerful it is, though it is powerful. Not because of how fast it goes, though it goes extraordinarily fast. But because of what it represents. It represents the solution to a physics problem so demanding, so merciless, that almost the entire vehicle is consumed just to deliver a tiny fraction of itself to the destination. Every kilogram of payload that reaches orbit was earned by burning dozens or hundreds of kilograms of fuel. Every satellite, every astronaut, every space station module was hurled upward on a column of fire that consumed the vast majority of the vehicle's mass during the ascent. And the reason for all of that is something we haven't fully explored yet. Something that turns a hard problem into a seemingly impossible one. Something that makes the relationship between speed and fuel not linear, not even quadratic, but exponential. The rocket equation. And that equation is where this story gets truly mind-bending. But before we get there, let's make sure one more thing is perfectly clear. There is no alternative to this, at least not for leaving Earth. On the surface of a planet with an atmosphere, you could theoretically use other methods. You could build a space elevator, a cable stretching from the surface to orbit, and climb it. You could use a giant electromagnetic launcher to fling objects into space. You could use a laser beam fired from the ground to heat air beneath the spacecraft, providing thrust without carrying fuel. These are all real concepts, some more practical than others, and we'll discuss them later. But none of them are ready for use today. And critically, none of them help you once you're already in space Once you're away from the ground and away from the atmosphere, once you're out there in the void, where there's no air and no ground and no laser hitting your spacecraft, the only way to change your velocity is to throw something out the back. There is no other known mechanism for propulsion in a vacuum that is practical for the speeds and masses involved in human spaceflight today. Ion engines, which we'll discuss later, work on the same principle. They throw particles backward. They just throw lighter particles at much higher speeds. Solar sails use photon pressure from sunlight. Photons carry momentum, so absorbing or reflecting them transfers momentum to the sail. But even this is just another version of the same principle. Momentum is being transferred from one thing to another. There is no magical drive that creates thrust from nothing. Conservation of momentum forbids it. The law says you cannot change the total momentum of a closed system. The only way to accelerate is to throw mass in the other direction. And if you're carrying that mass with you, you're subject to the tyranny of the rocket equation. That tyranny is what makes space travel so difficult. That tyranny is why rockets are almost entirely fuel. That tyranny is why every launch is a delicate balance of thrust and weight and timing, where a few percent change in the numbers can make the difference between orbit and failure. And that tyranny is what we're going to confront directly, because understanding it is understanding the single most important constraint on everything humanity has ever done or will ever do in space. Now, we need to confront the equation that governs everything we just talked about. And I want to be upfront with you. We're not going to write out formulas or do algebra. That's not what this is about. What we're going to do is understand deeply and intuitively why the relationship between speed and fuel is so punishing. Because once you grasp this, you'll understand why rockets look the way they do, why space travel is so expensive, and why getting anything to orbit is one of the hardest things humans have ever attempted. Let's start with an analogy. Imagine you're a hiker and you need to cross a vast desert. The desert is so large that you'll need food for the journey. But here's the problem. The food has weight. And carrying that weight requires energy, which means you burn calories faster when you're carrying a heavy pack, which means you need more food to sustain yourself on the journey. But more food means a heavier pack, which means you burn even more calories, which means you need even more food. See the problem? The food you need for the end of the journey has to be carried from the beginning. And carrying that food costs you food. So you need extra food to carry the food you'll eat later. And extra food on top of that to carry the extra food. And so on. If the desert is short, this isn't a big deal. You pack a few extra sandwiches and move on. But as the desert gets longer and longer, the amount of food grows faster and faster. It doesn't grow in proportion to the distance. It grows much faster than that. Double the distance, and you might need 3 or 4 times the food, not just twice. Triple the distance, and you might need 10 or 20 times the food. The relationship between distance and food is not linear. It curves upward, sharply, relentlessly, exponentially. This is exactly the problem a rocket faces. The desert is the velocity the rocket needs to achieve. The food is the fuel. The weight of the pack is the mass of the propellant. And just like the hiker, the rocket has to carry all its fuel from the very beginning of the journey. Fuel burned at the end of the mission had to be lifted off the launch pad, accelerated through the atmosphere, and hauled into space. Every kilogram of fuel that gets burned in the final seconds before reaching orbit was dead weight during the first minutes of flight. The rocket had to spend fuel to lift that fuel, and fuel to lift the fuel that lifted that fuel. This cascading requirement is the heart of the problem. In 1903, a Russian school teacher named Konstantin Tsiolkovsky published a paper that contained what is now called the Tsiolkovsky rocket equation. It is sometimes simply called the rocket equation. Tsiolkovsky was a remarkable person. He was largely self-educated, nearly deaf from a childhood illness that struck him at age 10, and spent most of his life teaching mathematics and physics in small Russian towns far from any major academic center. He had no access to a university laboratory. He had no wealthy patrons. He worked alone with pencil and paper, thinking through problems that the rest of the scientific world had barely considered. But he was also a visionary who dreamed of space travel decades before the Wright brothers flew the first airplane at Kitty Hawk. He worked out the mathematics of rocket propulsion from first principles, sitting alone in his study, imagining vehicles that wouldn't be built for another half century. And the equation he derived in that quiet room would come to govern every rocket ever launched. His equation describes the relationship between three things. Three quantities that together determine whether a mission is possible or impossible. The change in velocity a rocket can achieve, which engineers call delta V. The exhaust velocity of the engine, which measures how fast the propellant leaves the nozzle. And the mass ratio, which is the ratio of the rocket's total mass when fully fueled to its mass when all the fuel is gone. Let me explain the mass ratio because it's the key to everything. Imagine a rocket that weighs 100,000 kilograms when fully fueled. After it burns all its fuel, the empty rocket, including its engines, structure, and payload, weighs 10,000 kilograms. The mass ratio is 100,000 divided by 10,000, which equals 10. This means the rocket started out 10 times heavier than it ended up. 9/10 of its initial weight was fuel. Now, here's what Tsiolkovsky's equation tells us. The delta V the rocket can achieve is equal to the exhaust velocity multiplied by the natural logarithm of the mass ratio. The natural logarithm is a mathematical function that grows very slowly. The natural logarithm of 10 is about 2.3. So if your exhaust velocity is 4,000 meters per second and your mass ratio is 10, your delta V is 4,000 times 2.3, which is about 9,200 meters per second. That's just barely enough to reach low Earth orbit, and you achieved it by building a rocket that is 90% fuel by mass. 9 out of every 10 kilograms at liftoff is propellant that will be burned and expelled during the ascent. Now here's where the tyranny reveals itself. Let's say you want more delta V. Maybe you want to go to the moon or to Mars, or just carry a heavier payload to orbit. You need a higher delta V, so you need a higher mass ratio. But the logarithm function means the mass ratio has to increase exponentially to produce a linear increase in delta V. Going from 9,000 meters per second to 13,500 meters per second is an increase of 50% in delta V. But it requires the mass ratio to jump from 10 to roughly 30. You've gone from a rocket that's 90% fuel to one that's 97% fuel. That remaining 3% has to include everything. The engines, the fuel tanks, the guidance computers, the structural framework, and the payload. Everything that isn't fuel has to fit into 3% of the total mass. Push even further. Say you want 18,000 meters per second of delta V. That might be needed for a mission to Mars and back. The mass ratio would have to be about 90. That means the rocket at liftoff would need to be 90 times heavier than the empty vehicle. The fuel fraction would be over 98.9%. Only 1.1% of the total mass is available for everything else. At that point, building a rocket becomes almost physically impossible. You can't build fuel tanks that weigh almost nothing. You can't build engines out of thin air. The structural materials have to hold together under enormous forces. There's a practical limit to how light you can make the non-fuel components of a rocket. And the exponential nature of the equation slams you into that limit surprisingly fast. Let me try another analogy to make this exponential growth vivid. Imagine you're trying to fill a bathtub, but the bathtub has a hole in the bottom. Water is draining out as you pour it in. The bigger the hole, the faster water drains. And here's the twist. As you add more water, the hole gets bigger. So the more water you add, the more water you lose. So you need to add even more water to compensate. For a small bathtub, this is manageable. You pour fast enough and you fill it. But for a larger bathtub, the hole grows so fast that you need a fire hose. And for an even larger bathtub, you'd need a river. And eventually, for a bathtub large enough, no amount of water in the world could fill it because the hole is growing faster than you can pour. The rocket equation works the same way. For modest delta V requirements, you can manage with reasonable mass ratios. But as the delta V requirement grows, the mass ratio climbs faster and faster. And eventually it climbs so fast that building a vehicle becomes impractical or impossible with any known materials. Let me put real numbers on this to show you how quickly things escalate. Imagine you have a rocket engine with an exhaust velocity of 4,000 meters per second, which is typical for a good liquid hydrogen and liquid oxygen engine. If you want a delta V of 4,000 meters per second, you need a mass ratio of about 2.7. That means roughly 63% of your rocket is fuel. Manageable. A typical airplane is about 40% fuel by weight, so 63% is more, but not absurdly so. If you want 8,000 meters per second of delta V, you need a mass ratio of about 7.4. Now 86% of your rocket is fuel. That's getting demanding, but still buildable. If you want 12,000 meters per second, the mass ratio jumps to about 20. 95% fuel. Only 5% left for structure and payload. If you want 16,000 meters per second, the mass ratio is about 55. Over 98% fuel. Less than 2% for everything else. If you want 20,000 meters per second, the mass ratio is about 148. Over 99.3% of the rocket is fuel. The actual vehicle and payload are less than 1%. And reaching low Earth orbit requires about 9,400 meters per second of delta V. With an exhaust velocity of 4,000 meters per second, that demands a mass ratio of about 10.4, 90% fuel. That's the baseline. That's just to get to orbit. Anything beyond orbit requires even more fuel on top of that. Going to the moon requires additional delta V for translunar injection, lunar orbit insertion, landing, liftoff from the lunar surface, and return to Earth. The total delta V budget for an Apollo-style lunar mission was roughly 15,000 meters per second. At an exhaust velocity of 4,000 meters per second, the mass ratio required for the entire mission would be about 42. 97.6% fuel. That's why the Saturn V was so enormous. That's why it weighed nearly 3 million kilograms at liftoff. That's why the actual payload delivered to the lunar vicinity was about 1.5% of the total launch mass. The exponential nature of the rocket equation demanded it. But wait, there's something I glossed over that makes this even worse. I've been talking about the mass ratio as if the empty mass is just the structural weight plus payload. But it's not that simple. The fuel tanks themselves have mass. The bigger the tanks, the more they weigh. If you need more fuel, you need bigger tanks. Bigger tanks are heavier. Heavier tanks mean more total mass, which means you need even more fuel, which means even bigger tanks, which means even more weight. This is the same vicious cycle we discussed earlier, but now we can see it through the lens of the equation. The mass ratio isn't just about fuel versus payload, it's about fuel versus everything that isn't fuel. And everything that isn't fuel includes the tanks that hold the fuel, the engines that burn the fuel, the plumbing that feeds the fuel, the insulation that keeps the fuel cold, the structure that holds all of this together, and yes, the payload. Every one of these components has weight. Every kilogram of tank or engine or plumbing eats into your available mass ratio. The lighter you can make these components, the more of your mass budget can go to fuel or payload. This is why rocket engineering is so obsessed with weight reduction. Every kilogram matters. Every gram matters. Engineers will spend millions of dollars to shave a few kilograms off a fuel tank, because those kilograms ripple through the entire calculation. Save 1 kilogram on the tank, and you might save 3 kilograms of fuel, which means a slightly smaller tank, which saves a bit more fuel, which feeds back into the equation. The savings cascade just as the costs cascade. This is why aerospace engineers refer to the rocket equation as tyranny, not as a metaphor, as a technical description. The word tyranny has been used in official NASA publications. It is a genuine term of art in the industry. The equation is tyrannical because it dominates every single decision in rocket design. How thick to make the walls of the fuel tank, what material to use for the engine bell, whether to include a particular instrument on a spacecraft, whether an astronaut can bring an extra kilogram of personal items. Every single gram is evaluated against the rocket equation, because every gram that isn't fuel reduces the delta V the rocket can achieve, and every gram of additional delta V requirement demands exponentially more fuel. Let me give you a specific example of how punishing this is. Say you have a rocket designed to deliver a 1,000 kilogram satellite to low Earth orbit. The rocket has been carefully engineered with a specific mass ratio that gives exactly enough delta V to reach orbit with this payload. Now the customer comes back and says they want to add 100 kilograms to the satellite, just 10% more payload. How much additional fuel does the rocket need? If the relationship were linear, you'd expect about 10% more fuel. But it's not linear, it's exponential. Because the extra 100 kilograms of payload has to be lifted from the ground to orbit. Lifting it requires fuel. That fuel has weight, so you need fuel to lift the fuel. That additional fuel also has weight, and so on. When you work through the calculation, adding 100 kilograms to the payload of a typical orbital rocket might require adding 3,000 to 5,000 kilograms of additional fuel. A 10% increase in payload can require a 300 to 500% increase in fuel. This is the tyranny of the exponential. Small changes in the payload produce enormous changes in the fuel requirement, because the fuel has to carry itself, and each increment of fuel demands more fuel on top of it. This asymmetry between payload and fuel is the reason why launch costs are measured in thousands of dollars per kilogram. As of 2025, launching a kilogram to low Earth orbit on a Falcon 9 costs somewhere around $2,700. On older rockets, the cost was much higher, sometimes $10,000 to $20,000 per kilogram. Almost all of that cost is driven by the fuel, the vehicle, and the infrastructure needed to burn that fuel. The payload itself is almost an afterthought in terms of mass. It sits atop a column of propellant that outweighs it by a factor of 20 or 30 or more. This is why space launch is so expensive. It's not because rocket companies are greedy. It's not because the technology is unnecessarily complex. It's because the physics of the situation demands an enormous amount of fuel and hardware to deliver a relatively small payload. Every kilogram sent to orbit costs thousands of dollars, and most of that cost comes from the fuel and the vehicle that carries the fuel. The equation also explains why rockets are such unforgiving machines. In most engineering, you have margins. You build a bridge stronger than it needs to be because you might have underestimated the load or the materials might not perform perfectly. Engineers call this a safety factor. A typical bridge might be designed to handle 3 to 5 times its expected maximum load. This gives you a comfortable margin of error. Rockets don't have that luxury. Because of the exponential nature of the fuel requirement, adding mass for safety margins is prohibitively expensive. Every extra kilogram of structure added for safety requires multiple extra kilograms of fuel. Those extra kilograms of fuel require a bigger tank. The bigger tank adds more weight. And the cascading effect means that building in generous margins would make the rocket too heavy to reach orbit at all. This is why rockets operate on razor-thin margins compared to most other machines. A rocket engine might be designed to handle 1.2 times its expected maximum stress. Compare that to a bridge at 3 to 5 times. An airplane wing might handle 1.5 times its expected maximum load. A rocket engine is pushing closer to the edge because the equation won't allow the luxury of heavy-duty over-engineering. Now let's look at real rockets through the lens of the equation and see how their designers confronted this tyranny. The Saturn V is perhaps the most dramatic example. It was the rocket that carried Apollo astronauts to the moon between 1969 and 1972. It remains the most powerful rocket ever successfully flown. It stood about 111 meters tall, roughly the height of a 36-story building. At liftoff, it weighed approximately 2,950,000 kilograms. Of that, about 2,600,000 kilograms was propellant. The first stage, called the SIC, burned refined kerosene and liquid oxygen. It produced about 34 million newtons of thrust from its 5 F1 engines. Each F1 engine burned roughly 2,600 kilograms of propellant per second. All 5 together consumed about 13,000 kilograms per second. The first stage burned for about 2.5 minutes, and in that time, it consumed roughly 2,100,000 kilograms of fuel. 2,100,000 kilograms of kerosene and liquid oxygen burned in 150 seconds just to get the rocket to an altitude of about 68 kilometers and a speed of about 2,300 meters per second. After the first stage was spent, it was jettisoned. It separated from the rest of the rocket and fell back into the ocean. This is staging, and it's absolutely critical to the equation. We'll explore why shortly. The second stage, the S2, took over. It burned liquid hydrogen and liquid oxygen, a more efficient combination than kerosene and oxygen. It pushed the vehicle to an altitude of about 185 kilometers and a speed of about 6,900 meters per second. Then it too was jettisoned. The third stage, the S-4B, completed the push to orbit and later fired again to send the spacecraft on its way to the moon. By the time the Apollo spacecraft was on its way to the moon, over 98% of the Saturn V's original mass had been consumed or discarded. The SpaceX Falcon 9 tells a similar story with more modern numbers. It stands about 70 meters tall and weighs about 549,000 kilograms at liftoff. Its payload to low Earth orbit is about 22,800 kilograms. The mass ratio for the entire vehicle, including both stages, is about 24:1. That means for every kilogram of payload it delivers to orbit, the rocket needs about 23 kilograms of fuel and structure at liftoff. The Falcon 9's first stage uses 9 Merlin engines, burning kerosene and liquid oxygen. These engines produce exhaust at about 2,800 meters per second at sea level, increasing to roughly 3,050 meters per second in vacuum as the atmospheric pressure drops. The second stage uses a single vacuum-optimized Merlin engine with an exhaust velocity of about 3,400 meters per second. These exhaust velocities are good by chemical rocket standards, but they're still modest compared to the delta V required for orbit. The Space Shuttle was an interesting case study in the rocket equation's constraints. The shuttle orbiter itself weighed about 78,000 kilograms empty. It was a sophisticated winged spacecraft with 3 main engines, a cargo bay large enough to hold a school bus, and a heat shield capable of surviving re-entry at 25 times the speed of sound. But to get it to orbit, NASA had to strap it to an external tank holding about 735,000 kilograms of liquid hydrogen and liquid oxygen, plus 2 solid rocket boosters, each weighing about 590,000 kilograms. The external tank was taller than a 15-story building and held a volume of cryogenic propellant roughly equivalent to an Olympic-sized swimming pool. The total launch weight was about 2 million kilograms. All of that to deliver the 78,000 kilogram orbiter and up to 27,500 kilograms of cargo to low Earth orbit. The shuttle's payload fraction was about 1.4% when counting the cargo alone. If you count the orbiter itself as part of the delivered mass, since it had to reach orbit too, the fraction is higher, about 5%. But even 5% means 95% of the launch weight existed only to push the other 5% to orbital speed. Let me bring this home with one more way of thinking about it. Because the exponential nature of the equation is so counterintuitive that it really does bear repeating from different angles. Think of it like compound interest in reverse. With compound interest, your money grows exponentially because you earn interest on your interest. $100 at 10% annual interest becomes 110 after a year, 121 after 2 years, 133 after 3 years. The growth accelerates because the interest itself earns interest. With the rocket equation, your fuel requirement grows exponentially because you carry fuel for your fuel. The first kilogram of fuel carries the payload. The second kilogram carries the payload and the first kilogram of fuel. The third kilogram carries everything that came before it. Each new kilogram of fuel adds less and less effective push because a growing fraction of it is simply lifting other fuel. In both cases, the growth is driven by a quantity feeding back on itself. Interest earns more interest. Fuel requires more fuel. The mathematics are the same. It's exponential growth. And exponential growth always looks manageable at first, and then suddenly becomes overwhelming. If you want to save $1 million using compound interest at 10% per year, you need to invest about $385,000 and wait 10 years. The interest does some of the work for you. But the rocket equation is compound interest working against you. Every unit of delta V you want costs more than the previous unit because you have to carry the fuel for the later burns during the earlier ones. The first unit of delta V is cheap. The last unit is staggeringly expensive because by the time you burn it, you've already spent an enormous amount of fuel just carrying it to that point. This is the tyranny. This is why rockets are 90 to 99% fuel. This is why a vehicle the size of a building is needed to deliver a payload the size of a car. This is why every kilogram matters, why engineers agonize over grams, why rocket design is one of the most demanding disciplines in all of engineering. The equation doesn't care about cleverness or determination or budget. It is indifferent to ambition. It simply states with mathematical certainty that if you want to go fast by throwing mass out the back, and you have to carry that mass with you from the start, the fuel requirement grows exponentially with the desired velocity. And there is nothing, absolutely nothing, that changes this. You can build better engines, you can use lighter materials, you can optimize every component to the absolute limit of what physics allows, and the equation still dominates. It still demands that most of your vehicle be fuel. It still makes small increases in payload absurdly expensive. It still punishes any added weight with cascading fuel requirements. Better technology pushes the boundaries outward, but it doesn't change the fundamental shape of the curve. The curve is exponential, and exponential curves always win in the end. Engineers have found ways to work within this constraint to squeeze maximum performance out of every kilogram of fuel and structure. The most important of these solutions is staging, which fundamentally changes the game by throwing away structure as it becomes useless. But that's a story for what comes next. Because the rocket equation alone would be bad enough. What makes reaching orbit truly brutal is that the equation is only part of the problem. There are enemies waiting between the launch pad and orbit that make everything we've discussed so far even worse. Gravity pulls you down every second you climb. The atmosphere fights you with drag every meter you ascend. And these additional burdens pile on top of the exponential fuel demand in ways that push rockets to the very edge of what is physically possible. Everything we've discussed so far, the exponential fuel demand, the tyranny of the mass ratio, the punishing math of the rocket equation, all of that assumes a perfect scenario. It assumes you're in empty space, floating weightless, with nothing acting on you except the thrust of your engines. In that ideal case, every drop of fuel goes directly toward increasing your speed. Nothing is wasted. Nothing is lost. The equation is hard enough in that perfect vacuum. But real rockets don't launch in a perfect vacuum. Real rockets launch from the surface of a planet, and that planet is working against you in two very specific, very costly ways. The first enemy is gravity. Earth's gravity pulls everything downward at about 9.8 meters per second squared. That means for every second a rocket spends climbing, gravity is pulling it back down, stealing velocity. If you pointed a rocket straight up and fired the engine for 1 second, and the engine gave you 10 meters per second of upward velocity, gravity would immediately subtract 9.8 meters per second from that. Your net gain would be only 0.2 meters per second. 98% of the engine's effort in that moment went to fighting gravity rather than building speed. This is called gravity loss or gravity drag. It is not actual drag in the aerodynamic sense. There's no friction involved. It's the simple, constant, relentless pull of the planet on the rocket for every moment the rocket is climbing away from the surface. And it is enormously costly. Gravity never sleeps. It never takes a break. From the moment the rocket leaves the pad until it reaches orbit, gravity is pulling it backward. Even after the rocket clears the atmosphere and is soaring through near vacuum above 100 kilometers altitude, gravity is still there. It's weaker at higher altitudes, yes, but it's still substantial. At the altitude of the International Space Station, about 400 kilometers up, gravity is still about 88% as strong as it is on the surface. The rocket fights this pull for every second of its ascent, and every second of that fight costs fuel. Think of it this way. Imagine you're climbing a very tall ladder while someone hangs onto your ankles, pulling you down with a constant force. Every step you take, you're fighting their pull. If you climb slowly, you spend most of your energy fighting the person pulling you down and barely make any upward progress. If you climb quickly, you still fight the pull, but you spend less total time on the ladder. So the total energy lost to the pull is less. This is a crude analogy, but it captures the essential idea. Gravity loss depends on how long you spend fighting gravity. The longer your burn takes, the more velocity gravity steals from you. A rocket that takes 500 seconds to reach orbit loses more velocity to gravity than a rocket that does it in 300 seconds, assuming the same trajectory. This is why rockets need enormous thrust at liftoff. You might wonder why rockets don't just use smaller, more efficient engines and climb slowly. The answer is gravity loss. If the rocket climbs slowly, it would spend so much time fighting gravity that it would burn all its fuel before reaching orbit. The rocket needs enough thrust to not just hover, but to accelerate upward rapidly, minimizing the time spent in the gravity well. At liftoff, a typical rocket has a thrust to weight ratio of about 1.2 to 1.5. That means the engines produce 1.2 to 1.5 times the weight of the rocket in thrust. Only the excess above 1, that extra 0.2 to 0.5, actually accelerates the rocket upward. The rest just holds the rocket up against gravity. If the thrust to weight ratio were exactly 1, the rocket would hover, but not climb. Below 1, it wouldn't even leave the pad. It would sit there burning fuel, going nowhere, until it became light enough from burning fuel that the ratio exceeded 1. This actually happens briefly with some rocket designs during certain flight phases, and it's always a dangerous situation. How much velocity does gravity actually steal from a typical orbital mission? For most rockets launching to low Earth orbit, gravity losses account for about 1,000 to 1,500 meters per second of lost delta V. Remember, the total delta V budget for reaching low Earth orbit is about 9,400 meters per second, but the actual orbital velocity is only about 7,800 meters per second. That gap of roughly 1,600 meters per second is mostly gravity loss, with some contribution from the second enemy we'll discuss in a moment. 1,000 to 1,500 meters per second of velocity lost purely to fighting gravity during the climb. That is a staggering tax. Let me put it in perspective through the lens of the rocket equation. we established that the fuel requirement grows exponentially with delta V. Adding 1,200 meters per second of gravity loss to a mission that already requires 7,800 meters per second of orbital velocity might seem like a modest increase, about 15% more delta V. But because of the exponential relationship, that 15% increase in delta V can translate to a 30 to 40% increase in the required fuel mass. Gravity loss doesn't just add a little fuel, it adds an enormous amount of fuel because every additional meter per second of delta V requirement cascades through the exponential equation. There's a subtle additional cost to gravity loss that many people miss. The extra fuel needed to overcome gravity loss makes the rocket heavier at liftoff. A heavier rocket requires even more thrust to maintain an adequate thrust to weight ratio. More thrust means bigger engines. Bigger engines weigh more. Heavier engines eat into the mass ratio. A worse mass ratio means you need more fuel. And more fuel means an even heavier rocket. The cycle spirals again, with gravity loss amplifying the exponential tyranny of the rocket equation. The second enemy is atmospheric drag. Earth has an atmosphere. It extends from the surface to a gradual boundary with space at roughly 100 kilometers altitude, though there's no sharp line. The atmosphere near the surface is thick and dense. Air at sea level weighs about 1.2 kilograms per cubic meter. When a rocket pushes through this air at high speed, the air pushes back. This resistance is called aerodynamic drag, and it acts like a brake, slowing the rocket down. Drag depends on several factors: the speed of the rocket through the air, the density of the air, the cross-sectional area of the rocket, and the rocket's shape, captured by a number called the drag coefficient. The critical thing to understand is that drag increases with the square of velocity. If you double your speed, drag quadruples. If you triple your speed, drag increases 9 times. This means drag is relatively mild at low speeds, but becomes punishing as the rocket accelerates. At launch, the rocket is moving slowly and the drag is minimal. But within 60 seconds, the vehicle may be traveling at several hundred meters per second through air that is still fairly dense. The nose of the rocket slams into the atmosphere like a fist punching through water. Air molecules pile up in front of the vehicle, compressing into a shock wave that generates tremendous heat and pressure. The faster the rocket goes, the harder the air pushes back. In the first minute or so of flight, while the rocket is still moving relatively slowly and the atmosphere is thickest, drag is significant but manageable. The rocket pushes through the lower atmosphere at modest speeds, accumulating drag losses gradually. But as the rocket accelerates, there's a critical period called max Q, short for maximum dynamic pressure, when the combination of increasing speed and still thick atmosphere creates the peak aerodynamic stress on the vehicle. Max Q typically occurs about 60 to 90 seconds after launch at an altitude of roughly 10 to 15 kilometers. At this point, the atmosphere is thinner than at sea level, but still substantial, and the rocket is moving fast, often exceeding the speed of sound. The aerodynamic forces on the vehicle at max Q are enormous. The rocket structure must be strong enough to withstand these forces without buckling or breaking apart. And structural strength means structural weight. Every reinforcement, every thicker panel, every extra bolt that exists to handle max Q is weight that the rocket has to carry. Weight that eats into the mass ratio. Weight that the rocket equation punishes exponentially. Some rockets actually throttle down their engines as they approach max Q, reducing thrust to keep the aerodynamic pressure within safe limits. The Space Shuttle did this. Its main engines throttled down to about 65% of full thrust as the vehicle passed through the region of maximum dynamic pressure, then throttled back up once it was through. But throttling down means reduced acceleration, which extends the time spent in the atmosphere, which increases gravity losses. It's a trade off. Reduce drag forces by going slower, but pay for it with increased gravity loss. Or push through the atmosphere at full thrust, reducing gravity loss but increasing the structural requirements to survive the aerodynamic forces. Either way, you lose. The atmosphere extracts a price no matter what strategy you choose. How much does drag cost? For most orbital launches, aerodynamic drag losses account for about 100 to 500 meters per second of lost delta V, depending on the rocket's size, shape, and trajectory. This is smaller than gravity loss, but it's still meaningful. And like gravity loss, every meter per second of drag loss cascades through the exponential rocket equation, amplifying its cost in terms of fuel. Combined, gravity and drag steal roughly 1,200 to 1,800 meters per second from a typical orbital ascent. That means a rocket must carry enough fuel to produce 9,000 to 10,000 meters per second of delta V, even though the orbital velocity itself is only about 7,800 meters per second. Nearly 20% of the total propellant is burned just fighting gravity and air resistance, contributing nothing to the final orbital speed. 1/5 of all that fuel, all those thousands of kilograms of propellant burned in enormous engines, never adds a single meter per second to the spacecraft's orbital velocity. It's simply the tax that Earth's gravity and atmosphere charge for the privilege of leaving the surface. And because of the rocket equation's exponential nature, this 20% delta V tax translates to a fuel penalty much larger than 20%. The cascading effect means you might need 30 to 40% more total fuel mass just to cover these losses. Now, let's talk about the most important engineering solution ever devised to combat the tyranny of the rocket equation: staging. Because staging is not just a clever trick, it is the reason orbital spaceflight is possible at all with chemical rockets. Without staging, reaching orbit from Earth's surface would be essentially impossible using any known chemical propellant. Remember the mass ratio problem? The rocket equation says your delta V depends on the ratio of your full mass to your empty mass. Everything that isn't fuel, the tanks, the engines, the structure, counts as dead weight that reduces your effective mass ratio. Now, think about what happens during a launch. The rocket burns fuel. As the fuel is consumed, the tanks that held that fuel become empty. But those empty tanks are still there, still attached to the rocket, still being carried along. They're dead weight now. They serve their purpose holding fuel, but the fuel is gone and the tanks remain. They're dragging down the mass ratio for the rest of the flight. An empty fuel tank is like an empty backpack on a long hike. Once you've eaten all the food that was in it, the backpack itself is just useless weight on your shoulders. If you could throw the backpack away, you'd be lighter. You'd move faster. You'd need less energy for the rest of the journey. This is exactly what staging does. A multi-stage rocket is built in sections. Each section, called a stage, has its own fuel tanks and engines. When a stage has burned all its fuel, it is physically separated from the rest of the rocket and discarded. It falls away. taking its empty tanks and heavy engines with it. The next stage, already mounted on top, ignites its own engines and continues the ascent. But now it's working with a much better mass ratio because all that dead weight from the previous stage is gone. It's as if you've thrown away the empty backpack. Every kilogram of discarded stage is a kilogram that the remaining rocket no longer needs to push. And because the exponential nature of the rocket equation, discarding even a relatively small amount of dead weight produces a disproportionately large improvement in performance. Let me illustrate this with numbers. Imagine you have a single stage rocket that weighs 100,000 kilograms fully fueled, with structural and payload mass of 10,000 kilograms. That gives you a mass ratio of 10, which provides about 9,200 meters per second of delta V with a good engine. That's barely enough for orbit. Now imagine instead that you split this rocket into two stages. The first stage weighs 76,000 kilograms, fully fueled with 6,000 kilograms of structure. The second stage weighs 24,000 kilograms, fully fueled with 4,000 kilograms of structure and payload. The total mass is the same, 100,000 kilograms. But something magical happens. The first stage fires and burns its 70,000 kilograms of fuel. It achieves a certain amount of delta V, let's say about 5,000 meters per second. Then it separates and falls away. Now the second stage, weighing just 24,000 kilograms, ignites. Its mass ratio is 24,000 divided by 4,000, which is 6. With a good engine, this gives another 7,000 meters per second of delta V. The total delta V from both stages is about 12,000 meters per second, far more than the 9,200 meters per second the same total mass could achieve as a single stage. Same fuel, same total mass, but dramatically more delta V simply because you threw away the empty first stage rather than carrying it all the way to orbit. This is why almost every rocket that has successfully reached orbit has used staging. The Atlas rocket that carried John Glenn into orbit in 1962 was a stage and a half design that dropped its booster engines during ascent. The Saturn V used 3 stages. The Space Shuttle used 2 solid rocket boosters that separated after about 2 minutes, plus a main external tank that was jettisoned before reaching orbit. The Falcon 9 uses 2 stages, with the first stage separating and, in modern missions, flying back to land for reuse. The Soyuz, which has been carrying cosmonauts and astronauts to space since 1966 and remains in active service today, making it the longest serving crewed launch vehicle in history, uses a central core with 4 strap-on boosters that separate early in the flight, essentially creating a 2-stage or stage and a half configuration. The separation of those 4 boosters, visible in launch footage as they peel away from the central core in a distinctive cross pattern sometimes called the Korolev cross, after the legendary Soviet rocket designer Sergei Korolev, is one of the most visually recognizable moments in spaceflight. The Chinese Long March rockets use multiple stages. The European Ariane rockets use multiple stages. The Indian PSLV and GSLV use multiple stages. Japan's H-series rockets use multiple stages. Every spacefaring nation independently arrived at the same conclusion. Staging is universal because the physics demands it. There have been attempts to build single-stage to orbit vehicles, commonly abbreviated SSTO. The idea is appealing because a single-stage vehicle that doesn't discard anything could potentially be fully reusable, like an airplane that flies to orbit and back. No hardware is thrown away. No boosters splash into the ocean. The entire vehicle returns intact. But the rocket equation makes SSTO extraordinarily difficult with chemical propulsion. To reach orbit in a single stage, you need a mass ratio of at least 8 to 10 with the best available engines. That means the vehicle structure, engines, heat shield, landing gear, and payload all have to fit within 10 to 12% of the total launch mass. With current materials and engine technology, this leaves almost zero margin for payload. You could build a vehicle that reaches orbit, but it would have virtually no capacity to carry anything useful. The vehicle itself would be the entire payload. Experimental SSTO vehicles have been designed and partially tested. The McDonnell Douglas DCX, tested in the 1990s, demonstrated vertical takeoff and landing of a rocket vehicle, but never came close to reaching orbit. It flew to altitudes of only a few thousand feet. The British HOTOL concept and the more recent Skylon spaceplane proposal attempted to solve the problem by using air-breathing engines in the lower atmosphere and switching to rocket mode for the final push to orbit, essentially combining jet engine efficiency with rocket capability, but neither has been built. The Lockheed Martin X-33, a wedge-shaped prototype funded by NASA in the late 1990s, was intended to prove SSTO technology, but was cancelled in 2001 after persistent technical problems with its composite fuel tanks. Various studies over the decades have consistently shown that SSTO with chemical propulsion is technically possible, but commercially impractical because the payload fraction is so tiny. Staging remains the only viable approach for delivering meaningful payloads to orbit with chemical rockets. Let me explain one more aspect of staging that makes it so effective. When the first stage separates and the second stage ignites, the second stage isn't starting from rest. It's already moving. It inherited all the velocity the first stage built up. This means the second stage only needs to provide the remaining delta V to reach orbit. It doesn't need to repeat the work the first stage already did. And because the second stage is much lighter than the full stack, its mass ratio is better, and it can achieve a large delta V from a relatively small amount of fuel. The first stage does the heavy lifting. It fights gravity and dragging the thickest part of the atmosphere, while the rocket is at its heaviest. It burns through the majority of the fuel and gets the vehicle moving at 2,000 to 3,000 meters per second at an altitude above most of the atmosphere. Then it falls away, and the second stage takes over in a much more favorable environment. Less gravity loss because the rocket is already moving fast and spending less time climbing slowly. Virtually no atmospheric drag because the vehicle is above most of the air. And a much better mass ratio because the heavy first stage tanks and engines are gone. This division of labor is elegant and efficient. The first stage is optimized for the brutal environment near the ground. Massive engines with enormous thrust to fight gravity. Sturdy construction to withstand aerodynamic forces at max Q. Big fuel tanks to power through the dense lower atmosphere. The second stage is optimized for the relative calm of near vacuum. A single smaller engine optimized for vacuum efficiency with a larger nozzle expansion ratio that would be impractical at sea level. Lighter construction because there are no aerodynamic forces to withstand. A mass ratio that would be impossible to achieve if it also had to carry first stage hardware. Now, let's address something that constrains everything we've discussed: the limits of chemical propulsion. Chemical rockets work by combining a fuel and an oxidizer in a combustion chamber. The chemical reaction releases energy, which heats the resulting gas to extreme temperatures. That hot gas expands through the nozzle, converting thermal energy into kinetic energy, and exits at high speed. The exhaust velocity depends on how much energy the chemical reaction releases per kilogram of propellant and how effectively the nozzle converts that energy into directed motion. The most energetic chemical propellant combination commonly used in rocketry is liquid hydrogen and liquid oxygen. When hydrogen and oxygen react, they produce water vapor and release about 13.4 megajoules of energy per kilogram of propellant. This produces exhaust velocities of about 4,400 meters per second in a well designed engine. Can we do better? Not by much with chemistry. The hydrogen oxygen reaction is already close to the theoretical maximum for chemical energy release per kilogram. There are a few exotic combinations that release slightly more energy, such as fluorine and hydrogen, which can produce exhaust velocities a bit above 4,500 meters per second. But fluorine is horrifically toxic and corrosive. It reacts violently with almost everything, including the metal of the combustion chamber and nozzle. Using fluorine as a rocket oxidizer was explored in the 1950s and 60s, and abandoned because it was simply too dangerous and impractical. The engineering challenges of containing a substance that wants to dissolve everything it touches were insurmountable. Other exotic propellants have been studied. Compounds containing beryllium, lithium, or boron have theoretical advantages, but present equally severe practical problems, from extreme toxicity to solid combustion products that clog nozzles. The bottom line is that chemical propulsion is approaching a hard ceiling set by the energy density of chemical bonds. You can optimize engine design, improve nozzle efficiency, increase combustion chamber pressure, and refine propellant mixing. All of these produce incremental improvements, but the fundamental limit is the amount of energy stored in molecular bonds, and we're already using propellant combinations that are close to the theoretical maximum. This ceiling matters enormously because exhaust velocity is the lever that makes the rocket equation more or less forgiving. Higher exhaust velocity means you need less fuel for a given delta V. It shifts the entire exponential curve in your favor. If we could double the exhaust velocity from 4,000 to 8,000 meters per second, the mass ratio needed to reach orbit would drop dramatically. Instead of needing a rocket that's 90% fuel, we might need one that's only 60% fuel. Suddenly, single stage to orbit becomes practical. Heavy payloads become affordable. Deep space missions become routine. The entire economics of spaceflight would transform overnight. But chemical rockets cannot achieve 8,000 meters per second of exhaust velocity. It's physically impossible because there isn't enough energy in chemical bonds to accelerate the exhaust that fast. The energy is locked in by the laws of chemistry and thermodynamics, and no amount of engineering genius can extract more energy from a chemical reaction than the reaction contains. This is the fundamental constraint of chemical propulsion. It works, it's proven, it's reliable. We've built thousands of chemical rockets over the past 8 decades, but it will never be dramatically better than it already is. We're squeezing the last few percent of performance out of a technology that is approaching its physical limits. The exhaust velocities we achieve today are within maybe 10 to 15% of the theoretical maximum for any chemical propellant. There is no chemical miracle waiting to be discovered that will double or triple rocket performance. What this means practically is that the brute force approach, building ever larger rockets with ever more fuel, remains the primary strategy for chemical spaceflight. Want to send more mass to orbit? Build a bigger rocket? Want to go to the moon? Build a much bigger rocket. Want to go to Mars? Build an enormous rocket. Or find ways to refuel in orbit so you don't have to launch all the fuel from the ground at once. The rocket equation, combined with a fixed ceiling of chemical exhaust velocity, combined with the penalties of gravity and atmospheric drag, creates a box that chemical rockets cannot escape. Engineers have become extraordinarily good at operating within this box. Modern rockets like the Falcon 9 represent the pinnacle of chemical rocket optimization. But they cannot break free of the fundamental constraints. They can only work within them as cleverly as possible. This is why every rocket launch you see is such an achievement. It's not just a vehicle flying upward. It's a precision engineered response to one of the most demanding physics problems humans have ever faced. Every gram has been accounted for. Every engine has been tuned to extract maximum performance from its fuel. Every structural member has been designed to be as light as possible while still surviving the brutal forces of launch. The trajectory has been planned to minimize gravity and drag losses. The staging events have been timed to discard dead weight at the optimal moments. The entire machine exists at the razor edge of what physics allows. Because the rocket equation and its allies, gravity and drag, demand nothing less. So now you understand the full picture. A rocket moves by throwing mass out of its back end. Conservation of momentum demands this. There is no other way to accelerate in the vacuum of space. The fuel the rocket throws must be carried from the start, and carrying fuel requires more fuel, which requires more fuel, in an exponential spiral governed by the Tsiolkovsky rocket equation. On top of that, Earth's gravity steals velocity every second the rocket climbs, and the atmosphere imposes drag that the vehicle must push through. Staging helps by discarding dead weight, and chemical exhaust velocities are near their theoretical ceiling. All of these facts combine into a single, inescapable conclusion. Reaching orbit from the surface of Earth is one of the hardest things physics allows. Not hard in the way that building a bridge is hard, where the challenges are practical and can be solved with bigger beams and more concrete. Hard in the way that a fundamental law of nature makes it hard. The difficulty is baked into the universe itself. Engineers and physicists have spent more than a century trying to find ways around this constraint, or at least ways to soften it. Some of these ideas are brilliant, some are wildly impractical, some might work someday, but all of them exist in the shadow of the rocket equation, because the equation doesn't go away just because you wish it would. It sits there, patient and immovable, governing every proposal, every design, every dream of reaching space more easily. Let's start with the most obvious approach. If the problem is that chemical exhaust velocities are too low, then use something with a higher exhaust velocity. This is the idea behind electric propulsion, and it actually works. Ion engines and Hall effect thrusters use electric fields to accelerate charged particles, usually xenon ions, to exhaust velocities of 20,000 to 50,000 meters per second. That is 5 to 12 times higher than the best chemical rockets. With exhaust velocities that high, the rocket equation becomes far more forgiving. The mass ratios needed for a given delta V drop dramatically. A spacecraft using ion propulsion can achieve enormous total delta V with relatively modest amounts of fuel. There's a catch. There's always a catch. Ion engines produce very little thrust. A typical ion engine might produce about 0.1 to 1 newton of force. For comparison, a single space shuttle main engine produced about 2 million newtons. An ion engine produces roughly 20 million times less thrust than a chemical rocket engine. This means ion engines can't fight gravity. They can't lift off from a planet. They can't even hover. If you strapped an ion engine to a spacecraft sitting on a launch pad and turned it on, absolutely nothing visible would happen. The thrust is so low that it would take the engine days to accelerate the spacecraft by even 1 meter per second. Gravity would pin it to the ground effortlessly. Ion engines work only in space, where there is no gravity well to climb out of and no atmosphere to push through. Once a spacecraft is already in orbit, delivered there by a conventional chemical rocket, an ion engine can slowly, patiently accelerate it over weeks or months, building up enormous velocities through continuous gentle thrust. NASA's Dawn spacecraft used ion propulsion to visit the asteroid Vesta and then the dwarf planet Ceres, achieving a total delta V of about 11,000 meters per second over the course of its mission, far more than any chemical spacecraft of comparable size could have managed. The Dawn spacecraft carried only about 425 kilograms of xenon propellant, yet achieved velocity changes that would have required many thousands of kilograms of chemical fuel. The trade-off was time. Dawn took years to build up that velocity, firing its ion engines for thousands of hours in gentle, sustained burns. The European Space Agency's Smart 1 mission used ion propulsion to spiral slowly outward from Earth orbit to lunar orbit over the course of about 13 months. A chemical rocket can make the same trip in 3 days, but the Smart 1 mission demonstrated that ion engines could get there using a fraction of the fuel. Japan's Hayabusa missions used ion engines to travel to asteroids, collect samples, and return them to Earth. These missions demonstrate that ion propulsion is real, proven, flight-tested technology that works exactly as the physics predicts. But it doesn't solve the fundamental problem of getting off Earth. For that, you still need chemical rockets or something equivalently powerful. Ion engines are a solution for deep space, not for launch. Nuclear thermal propulsion is another approach that has been seriously studied. The concept is straightforward. Instead of burning chemical fuel, you use a nuclear reactor to heat a propellant, usually liquid hydrogen, to extremely high temperatures, then expel it through a nozzle. Because the energy comes from nuclear fission rather than chemical bonds, you can heat the hydrogen to much higher temperatures than any chemical reaction could achieve. Hotter gas means faster exhaust. Nuclear thermal engines could theoretically achieve exhaust velocities of about 8,000 to 9,000 meters per second, roughly double what chemical engines produce. Doubling the exhaust velocity would dramatically improve the rocket equation. Mass ratios for orbital missions would drop. Payload fractions would increase. Deep space missions that currently require enormous vehicles might become achievable with much smaller ones. A mission to Mars, which requires a total delta V of roughly 6,000 meters per second beyond low Earth orbit, would need far less fuel with nuclear thermal propulsion than with chemical engines. This isn't science fiction. NASA actually built and tested nuclear thermal rocket engines in the 1960s and early 1970s under a program called NERVA, which stood for Nuclear Engine for Rocket Vehicle Application. Engineers at the Los Alamos Scientific Laboratory and the Aerojet Corporation designed and tested multiple nuclear rocket engines. The most advanced, the Pewee engine, ran successfully in ground tests, demonstrating that the technology works. The engines heated hydrogen propellant to about 2,500 degrees Kelvin, using a solid core nuclear reactor, achieving exhaust velocities of about 8,300 meters per second. The program was cancelled in 1973, not because the technology failed, but because of budget cuts and shifting political priorities after the Apollo program wound down. At its peak, the NERVA program had demonstrated reactor runtimes of over an hour and multiple restart capability, both essential requirements for a practical space engine. The engineers involved believed they were within a few years of a flight-ready engine when the funding was pulled. It remains one of the great what-ifs of space exploration. Had NERVA continued, human missions to Mars might have been achievable in the 1980s using nuclear thermal propulsion, decades ahead of current plans. There has been renewed interest in nuclear thermal propulsion in recent years. NASA and the Defense Advanced Research Projects Agency, known as DARPA, announced a joint program in 2023 called DRACO, which aims to demonstrate a nuclear thermal rocket engine in orbit by the late 2020s. If successful, this could open the door to faster and more fuel-efficient missions to Mars and beyond. But nuclear thermal propulsion still doesn't solve the launch problem. You wouldn't use a nuclear reactor to launch from Earth's surface. The risk of a launch failure scattering radioactive material across the landscape is too severe. Nuclear thermal engines would be used in space after a conventional chemical rocket has delivered the spacecraft to orbit. So, once again, chemical rockets remain the gatekeepers. They're the only proven way to escape Earth's surface, and the rocket equation governs every one of them. What about not carrying your fuel at all? This is perhaps the most radical approach to cheating the rocket equation, and several concepts explore it. A space elevator is one such idea. Instead of launching rockets, you build a cable from the Earth's surface to geostationary orbit, roughly 35,800 kilometers above the equator. An electrically powered climber vehicle ascends the cable, carrying payload to orbit without any rocket fuel whatsoever. The energy comes from the electrical grid on the ground, transmitted to the climber through the cable or by laser. No exhaust, no mass ratio problem, no rocket equation at all. The concept is elegant and the physics is sound. Arthur C. Clarke popularized the idea in his 1979 novel, The Fountains of Paradise, though the concept was first proposed by Konstantin Tsiolkovsky himself back in 1895. A geostationary orbit is the altitude where the orbital period matches Earth's rotation. So a cable anchored at the equator and extending to that altitude would remain taut, held by the balance between gravity pulling the lower portion down and centrifugal force pulling the upper portion outward. You could ride an elevator to space the way you ride an elevator to the top floor of a building. No fuel, no roaring engines, just a smooth, steady climb lasting perhaps a week. The problem is materials. The cable would need to be incredibly strong and incredibly light. The tension on it would be enormous, far beyond what any existing material can handle at practical thicknesses. Carbon nanotubes have been proposed as a material strong enough to make a space elevator possible. They have theoretical tensile strengths roughly 100 times greater than steel at a fraction of the weight. But we cannot yet manufacture carbon nanotubes in continuous strands longer than a few centimeters. Building a cable 35,800 kilometers long from carbon nanotubes is currently beyond our manufacturing capability by many orders of magnitude. It may become possible in the future, but it is not possible today, and will not be possible for decades at least, if ever. The engineering challenges beyond just the cable are also formidable. How do you protect the cable from orbital debris impacts? A single collision with a piece of space junk could sever the cable catastrophically. How do you handle weather, especially lightning strikes and hurricanes, near the equatorial anchor point? How do you manage the oscillations and vibrations that would travel up and down a cable tens of thousands of kilometers long? These are not trivial problems. Laser propulsion takes a different approach. Instead of carrying fuel, a spacecraft carries a large reflective surface, essentially a giant mirror or sail. A powerful laser on the ground fires a beam at the sail, and the pressure of the photons pushes the spacecraft forward. The energy stays on the ground. The spacecraft carries no fuel. The rocket equation does not apply because the spacecraft isn't expelling mass. The Breakthrough Starshot initiative, proposed in 2016 by physicist Stephen Hawking and investor Yuri Milner, uses this concept at a small scale, proposing to accelerate gram-scale spacecraft to 20% of the speed of light using ground-based lasers. For larger, heavier spacecraft capable of carrying humans or significant cargo, the laser power required becomes enormous, on the order of gigawatts or tens of gigawatts, focused into a tight beam that must track a moving target with extreme precision. The technology for generating and directing such beams doesn't exist yet, though the physics is well understood. There's also the concept of beam-powered launch, where a ground-based laser heats air or a propellant beneath a vehicle, providing thrust without the vehicle needing to carry its own energy source. Like craft, small experimental vehicles have been launched to modest altitudes using this technique in laboratory demonstrations. But scaling this to orbital velocities and meaningful payload masses would require laser installations of unprecedented power and precision. None of these beam-powered approaches are ready for operational use, but they represent genuine attempts to sidestep the rocket equation by separating the energy source from the vehicle. Orbital refueling is a more near-term approach that works within the rocket equation rather than trying to escape it. The idea is simple. Instead of launching a fully fueled spacecraft from Earth in a single enormous rocket, you launch the spacecraft empty or partially fueled and then send up additional fuel on separate, cheaper launches. The spacecraft refuels in orbit and then departs for its destination. This doesn't change the rocket equation for any individual launch. Each launch to orbit still requires the same punishing mass ratio, but it changes the overall mission architecture by breaking a single, impossible launch into several difficult but achievable ones. SpaceX's Starship architecture depends heavily on this concept. The Starship vehicle is designed to reach low Earth orbit, then be refueled by multiple tanker flights before departing for the Moon or Mars. A single Starship might need 6 to 12 tanker flights to fill its tanks in orbit, depending on the mission. Each tanker launch is a standard orbital mission subject to the rocket equation, but by refueling in orbit, the Starship can carry far more propellant for its deep space burn than it could if it had to launch with all that fuel from the ground. NASA's Artemis program for returning astronauts to the moon also incorporates orbital refueling as a key element, recognizing that breaking the mission into segments is more practical than trying to accomplish everything in a single launch. This approach is practical and is being actively developed. It doesn't cheat physics. It works with physics by cleverly distributing the fuel burden across multiple launches. There's a deeper point here that's worth making explicit. The rocket equation is not a problem to be solved, it is a law of nature to be respected. Every approach we've discussed, from ion engines to nuclear thermal rockets to space elevators to laser propulsion to orbital refueling, is an attempt to work around the equation or to change the terms of the equation in favorable ways. Ion engines change the exhaust velocity term, making it much higher, which improves the mass ratio. Nuclear thermal engines do the same thing, though less dramatically. Space elevators and laser propulsion remove the need to carry propellant entirely, eliminating the mass ratio problem altogether. Orbital refueling accepts the mass ratio, but distributes it across multiple vehicles. Each approach has merit, each has limitations. None of them makes the equation go away. The equation is a consequence of conservation of momentum, and conservation of momentum is one of the most fundamental principles in all of physics. It has never been violated in any experiment, under any conditions, at any scale. It holds for subatomic particles and for galaxies. It holds at absolute zero and at billions of degrees. It holds in the weakest gravitational fields and in the strongest. There is no known exception and no theoretical reason to expect one. As long as momentum is conserved, rockets must expel mass to accelerate, and the exponential relationship between velocity and fuel will persist. This brings us to something that I think is worth reflecting on. The fact that rockets need so much fuel is not a failure of human engineering. It is a testament to how close human engineering has come to the limits of what physics allows. When you watch a Falcon 9 launch, or a Soyuz, or an Ariane, or any orbital rocket, you're watching a machine that operates within a few percent of the theoretical maximum performance allowed by its propellant chemistry. The engines extract nearly all the available energy from the chemical reaction. The nozzles expand the exhaust to nearly optimal velocities. The structures are built as light as materials science permits. The trajectories are computed to minimize losses from gravity and drag. There is very little performance left on the table. The engineers have done almost everything that can be done within the constraints of chemical propulsion. The reason we can't just easily fly to space is not that our rockets are bad. Our rockets are extraordinary. It's that the physics of the problem is extraordinarily demanding. Reaching orbital velocity from the surface of a planet with an atmosphere and a significant gravitational field, using onboard propellant expelled from a nozzle, is inherently, unavoidably, mathematically expensive. The rocket equation says so. And the rocket equation, unlike budgets and schedules and political priorities, does not negotiate. Consider what this means for the future of humanity in space. Every kilogram that reaches orbit was lifted there by the brute force expenditure of chemical energy, fighting gravity and drag, and the exponential tyranny of the mass ratio every meter of the way. The International Space Station, which weighs about 420,000 kilograms, was launched piece by piece over more than a decade, carried to orbit on dozens of rocket flights. Each flight burned hundreds of thousands of kilograms of propellant. The total fuel burned to assemble the station in orbit was many millions of kilograms. All of that fire and thunder and engineering brilliance, and the result is a structure about the size of a football field floating 400 kilometers above the Earth. It's magnificent. It's arguably the greatest engineering achievement in human history. But it also illustrates the cost of working within the rocket equation. Every bolt, every panel, Every piece of equipment on that station was purchased at the price of enormous quantities of fuel burned in enormous rockets. Going forward, everything humanity does in space will be shaped by this constraint. Missions to the moon, to Mars, to the asteroids, even maintaining satellites in orbit, all of it is governed by the rocket equation. The cost of space launch is fundamentally driven by the fuel needed to reach orbital velocity. And that fuel requirement is set by physics, not by market forces or government budgets. Reducing launch costs means either reducing the amount of hardware that is discarded during launch, which is what SpaceX has done with reusable first stages, or increasing the number of launches to spread fixed costs, or developing new propulsion technologies that change the terms of the equation. Reusability is perhaps the most significant practical development in recent decades. When SpaceX successfully landed a Falcon 9 first stage in 2015, it was a moment that changed the space industry. It demonstrated that the most expensive part of a rocket, the engines and avionics of the first stage, could be recovered and flown again. This doesn't change the rocket equation. The Falcon 9 still needs the same amount of fuel and the same mass ratio to reach orbit, but it dramatically changes the economics because you don't have to build a new first stage for every launch. Instead of throwing away a $100 million piece of hardware after every flight, you refurbish it and fly it again. SpaceX has now flown individual Falcon 9 first stages over 20 times each. This reuse has brought launch costs down substantially and demonstrated that the economic barrier to space, if not the physical barrier, can be reduced through engineering ingenuity. But reusability has limits too. This second stage of the Falcon 9 is still expendable, discarded after every flight. Recovering the second stage is much harder because it reaches orbital velocity and must survive re entry at much higher speeds. SpaceX's Starship is designed to be fully reusable with both the first stage, called Super Heavy, and the upper stage, called Starship, returning to land after every flight. If this succeeds, it could reduce launch costs by another order of magnitude, potentially bringing the cost per kilogram to orbit down to a few $100s. But even at a few $100s per kilogram, the total cost is still driven by the sheer mass of fuel required. A Starship launch will burn roughly 4,700 metric tons of propellant, over 10 million pounds. At current prices for liquid methane and liquid oxygen, the fuel alone costs somewhere around $1 to $2 million per launch. That's a flaw that no amount of engineering can lower much further because it's set by the cost of the chemicals themselves. Let me bring this full circle. We start tonight with a simple question. Why do space rockets need so much fuel? And the answer turns out to be one of the most elegant and humbling truths in all of physics. Rockets need so much fuel because they must carry their propellant with them. They move by expelling that propellant backward, which pushes them forward. This is the only way to move in the vacuum of space. But carrying propellant adds mass. More mass requires more propellant. More propellant adds more mass. This self-reinforcing cycle produces an exponential relationship between velocity and fuel, captured precisely by Tsiolkovsky's rocket equation. The equation shows that to reach orbital velocity, which is about 9,400 meters per second, when you include losses from gravity and atmospheric drag, a chemical rocket must be roughly 90% propellant by mass. For missions beyond orbit, the percentage climbs even higher. This is not a limitation of our technology. It is a limitation of our universe. The speed of light limits how fast we can communicate. The laws of thermodynamics limit how efficiently we can convert energy, and the rocket equation limits how efficiently we can travel through space using onboard propellant. These aren't engineering problems waiting to be solved. They're features of the cosmos we inhabit. And yet, despite all of this, we do it. We build these impossible machines. We fill them with millions of kilograms of propellant. We light them on fire and ride them to orbit. We've sent humans to the moon. We've sent robots to Mars, to Jupiter, to Saturn, to the edge of the solar system. We've built a space station that has been continuously inhabited for over 24 years. We've launched telescopes that can see galaxies 13 billion light years away. All of it accomplished within the merciless constraints of the rocket equation. Every rocket launch is a confrontation with one of nature's harshest truths. And every successful launch is a victory. Not over the equation, because you don't defeat a law of nature, but within it. We've learned to work inside the box that physics gives us. We've learned to squeeze every possible gram of performance from our machines. We've learned to stage our rockets, optimize our trajectories, reuse our hardware, and refuel in orbit. We've turned the tyranny of the rocket equation from an insurmountable barrier into a solvable, if demanding, engineering challenge. That is the story of rocketry. Not a story of escaping the equation, but of learning to live with it, of building machines so extraordinary, so precisely optimized, so carefully engineered that they can deliver a payload to orbit, even though the physics says it should be nearly impossible. Every time you see a rocket rise from the pad on a pillar of flame, trailing a thunderous roar that you can feel in your chest from miles away, you're witnessing something remarkable. You're watching human beings negotiate with the laws of physics and win. Not by breaking those laws, not by cheating them, but by understanding them so deeply, so thoroughly, that we can work within their constraints to achieve something that would have seemed like pure magic to every generation of humans that came before us. The rocket equation doesn't care about our ambitions. It doesn't care about our dreams of reaching Mars or building cities on the moon or traveling to other stars. It simply states, with cold mathematical certainty, that if you want to go fast by throwing stuff out the back, you had better bring a lot of stuff to throw. And the faster you want to go, the more stuff you need, not in proportion, but exponentially, mercilessly, unavoidably. That's the truth. That's why rockets are 90% fuel. That's why they're so enormous and so expensive and so spectacular. And that's why every successful launch, every satellite in orbit, every astronaut floating in microgravity represents one of the greatest achievements of the human species. Not because it's easy, because it's hard, because the physics is unforgiving, and because we do it anyway. The next time you watch a rocket launch, whether it's on a screen or in person, remember what you've learned tonight. That massive vehicle sitting on the pad is almost entirely fuel. The payload at the top, the thing the whole mission exists to deliver, is a tiny fraction of the total mass. The engines at the bottom will burn through millions of kilograms of propellant in a matter of minutes, converting chemical energy into kinetic energy with extraordinary efficiency. The vehicle will shed stages along the way, discarding empty tanks and spent engines to lighten the load. Gravity will pull it down. The atmosphere will push it back. The rocket equation will demand its exponential toll. And yet, despite all of that, the payload will reach orbit. A small, precious piece of human ingenuity, carried to the edge of space on a column of fire, delivered into the void through sheer force of physics and engineering. That's what rockets do. That's why they need so much fuel. And that's why every single one of them is a miracle of human determination operating within the most unforgiving equation in all of engineering.